Hey guys, today we're going to talk about a product that's fairly new to the battery marketplace. This is the DIY battery kit from sunfunkits.com. So what this company has basically done is they provide all the materials you need to assemble and build your own lithium iron phosphate battery. So that includes any hardware, bus bars, mounting brackets, BMS, wiring. So they sent me out this kit for review and evaluation. We're going to take a look at what we got, build, assemble, and test our own battery, and see what we think. This kit is really centered around the EVE 280 amp hour lithium iron phosphate batteries. I have 4 of them here. They do sell these batteries, or you can provide these yourself. And I'm told it also works with the Lithium 272 amp hours and some of the cattle cells, pretty much any cell that's in this form factor. So I've also got a BMS, bag of hardware. Got 6 rigid bus bars here. We've got a set of cables with Anderson 175 amp connectors on the end. We have 3 smaller cables for connecting the battery to the BMS and connecting the BMS to the terminals. And here we have a small passive balancer. I believe this was 1.2 amp. And we also have a set of balancing leads, both for this balancer and for the JBD BMS. We have the handles for the battery enclosure, 2 bus bars to connect your battery to, and we also have several various size brackets to fit various size cells and BMS configurations. And they also provide a very nice set of detailed instructions, so we're going to get right to it. So first, a quick inspection of the batteries themselves. These are EVE 280 amp hour. I believe these were the LF280N variant. So looking how they sit together here, you can see they are all flat. They are perfect batteries. There's no bulging or anything like that. So looking at the top here, we have the original caps from EVE, positive and negative. Terminals look good. I don't see any sign of actually having been used. There are M6 threads bored on them, which is fairly standard for this particular variant of battery. And getting a closer look here, we can see the original QR code is intact and looks good. There's no corrosion or anything on the vent. That's not damaged. That looks good as well. Looking at the actual enclosure, this is a standard plastic enclosure that we see a lot of batteries getting built in. And this is modified just a little bit. We have a piece of aluminum U-channel on the left and the right. In addition, there is a piece of, I don't know, that's about 3/4 inch thick, some very rigid foam on the inside here. So the instructions indicate the first thing you should do is top balance your cells. And there's a link to a video that explains the process. I'm not going to worry about doing this because I want to see how they ship, but if you're building one yourself, I strongly recommend following the instructions as documented. Alright, so the instructions indicate which orientation these cells need to go in, and they do recommend putting the 2 end cells in first because this foam is going to squeeze inward just to prevent these cells from moving around, so you will have to wiggle them in a little bit. Oh, that is a nice fit. Look at that. I don't know if I can fit that in or not. Alright. I really had to lay on that to get that cell in, but that is a nice fit in there. Look at that. It fits tightly up against both aluminum U-channels. There's no space between the cells at all. So I guess that foam there is a little bit of room for them to expand and contract in the middle of the cell. Shouldn't have to worry about the top part moving at all, so it's good that this aluminum is holding it in place. So we're just going to double check here that we have these in the correct polarity and orientation, because the idea is these are all going to be connected in series to form 12 volts. So I'm going to check the markings on the cell in addition to the plastic covers, because these plastic covers obviously can get swapped and we don't want to make a mistake. So from left to right on the top I have negative, positive, negative, positive. On the bottom I have positive, negative, positive, negative. Perfect. And we can see the exact orientation documented here on page 5. There are different size spacers here. You can see the yellow one's got a wider space than the red one. This red one is designed for these EVE 280N cells, so we're going to use the red spacer. And then we've just got 4 of these black screws with a silver washer. It's a hex screw. Just thread into each of the 4 corners like so to hold this top plate down, keep the cell secured. This is 3D printed. They 3D print these themselves. I believe this is PLA material. I'm not too familiar with 3D printing myself, but it sounds like they've tested it up to 140 or 145 degrees Fahrenheit, I believe it was. Now page 6 says that you need to use thread locker, such as Loctite, in these terminals. They recommend blue Loctite. Unfortunately, the only Loctite I have currently is red 271, which is, red tends to be permanent. You need heat to remove it, whereas blue is removed with common tools. I don't want to put red permanent sealant in these just yet. So I'm going to skip this step for the time being for the sake of this video. And then I need to go out and purchase some blue Loctite, and we'll Loctite these later. So next we're ready to install our bus bars. We do have extra bus bars here because these are intended to be used for the parallel connections if you're top balancing. We will only need 3 bus bars for this. Anytime you do something like this, you definitely want a pair of safety glasses. And I'm going to very carefully set the bus bars in place. Alright, so we've got a rather large bag of hardware here. So there are 2 ways we can connect these bus bars to the battery. First method is with these threaded grub screws, I believe they're called. So you would thread this into the battery, and then we have a serrated flange nut that you would tighten down, and that would form your battery post, your stud in each battery. And this is the method most people use when they're assembling these EVE batteries. The company building this kit has also provided these screws. I believe they are 8 millimeters in length, and they measured these out to be the perfect size to use as many threads as possible in these batteries without having these screw bottom out. So I think I'm going to use these screws, and the reason for that is simply if I put the stud on here, it's going to stand up, an inch or so above the battery, whereas the screw fits near flush with this bus bar. Obviously the head of the screw sticks up a little bit, but in the event you're using cells that have studs on, this kit can accommodate cells with studs on, but then they include this spacer piece, and the spacer piece would sit on top of the battery, like so, and then your lid would simply fit on top of the spacer piece. So that just adds a little bit of extra height to your enclosure to compensate for those studs. To avoid the need for this space piece, since we have batteries with threaded holes, I'm going to use the screws. That way everything sits flat and I do not need to use the spacer piece. So I'll put a washer on each screw and just thread them in loosely by hand. Alright, so we have 2 sets of balance leads here. One goes for the BMS, and the second one goes for the small passive balancer. And the way these work is you'll see each lead has a red and a black, and then there's several wires in between. So we're going to start with the reds of each connector, and they'll go to the main positive. So the next wire from each connector will go to the first series connection, all the way until we get to both black wires, which will go to the main negative pole of the battery. I don't know guys, when I tighten down this bolt over here on the far right, it feels really good, like it's nice and tight, but this one on the left here that's got 2 ring terminals on, it feels like it's going to strip as I tighten it down. And so if you don't know, on these EVE cells, these are aluminum posts, and these threads are aluminum, and it's very, very easy to strip out aluminum threads. I don't want to do that because once I do that, these cells are ruined and there's really no way to use them after that. You can see here, once I pile on 2 ring terminals, the washer, and then I put the bus bar, there's very few threads there to actually grab into the cell. So I do think I'm going to switch this to using these studs instead of the screws and see what happens. And the way that works here is I'll simply thread this screw the entire way down, then I'll put my washer on, then both of my ring terminals, and then I will thread down the nut. And that feels much better tightening. Alright, so now I'm up to the main negative connection here. And before I can put the nut on here, we need to install our cable that's going to go from the battery to the BMS, and that is this blue cable that is in a Y shape with 3 lugs here. So obviously the single lug will go on the battery post, the lug will go on first, then both ring terminals, and then the flange nut. Order is very important here. You want this lug to go against the battery itself. You don't want to have anything like a washer or a ring terminal between the battery pole and the lug. And we'll do the same on the positive, but we have this smaller red jumper, and this makes me a little bit nervous here because this is positive and I don't want it to short against terminal back here, so I'm being very careful at how I position this. Alright, so the instructions here say the tightness of these bolts should be 6 to 8 Newton meters. 6 Newton meters is approximately 54 inch-pounds. So I got my torque wrench here. I'm just going to set it to 55 inch-pounds, which is the lower end of the spectrum. And of course, for safety, this is an insulated torque wrench. There we go. Alright, so I know the instructions say 6 to 8 Newton meters. But I actually ended up backing this down to 45 inch-pounds, which is approximately 5.2 newton meters, because the way I was doing it before, at approximately 6 newton meters or 55 inch-pounds, really didn't feel good on these aluminum posts. You know, I felt like they were starting to strip, even though that's within spec according to the instructions, so I don't know. 45 inch-pounds is closer to what I used in my own battery bank when I built that, so that's what I'm going to stick with here. So next I want to use my voltmeter just to measure these balance connectors and make sure they are, the polarities are correct and in the correct order. Otherwise I'll risk blowing up my BMS or my balancer, and I don't want to do that. I'm going to put the negative on the main negative lead, and I'll just go up the wires one by one, and I should see the voltage increasing on the display. So the black one should be 0, and I've got 3 volts, 6 volts, 9 volts, and 13 volts. So I know these are in the correct order, and I'll check the other one the same way. So this square yellow piece will be my spacer for the BMS, and I'll sit that right on top like so. Before I do that, I think I want to neaten up some of these wires a little bit here. Alright, so that's not much neater, but it's at least preventing these wires from rubbing on any opposing bus bars. Now I'm ready to install this plastic spacer piece, and I can also sit down the BMS, and these long black bolts will go through the BMS board, through the spacer, and then down into the nut plates on the bracket that's holding the cells in place. I should note too, this BMS is a JBD BMS. That's a high quality BMS. It's the same BMSs that Current Connected is selling. I believe Overkill Solar and Battery Hookup are JBD as well. This particular one is rated for 150 amps continuous power, so it's plenty powerful for this battery. Alright, so next I'm ready to secure these 2 negative leads to the B- terminals of the BMS. And you can see the instructions here, how they have the leads routed around the aluminum plate on this BMS, I guess to avoid the potential of this plate rubbing through these wires. But there really isn't enough room on these wires. They're bent at like obscure angles, so I'm just going to try my best to do that here. Alright, so at the top here I'm just securing the Bluetooth module with a zip tie. So they actually recommend in the manual to affix this with double-sided tape. Alright, so next we're ready to connect the final output terminals. Now the instructions recommend not plugging in this balance lead until this step is complete. I'm guessing to avoid accidentally shorting out this positive to these terminals over here, because keep in mind this BMS is shut off while this lead is removed. So I should not see any voltage on these 2 terminals, but I'm still going to use caution as appropriate just in case. And to do that I'm using this smaller black lead, and this is installed with the flat side of this ring terminal up, so it's going to go on just like this. Alright, and I see why they say not to attach the balance lead yet, because it's very easy to go oops when you're installing this and short this battery out, and I certainly don't want to do that. So next step is to attach the terminals to this lid before we attach that BMS balance lead. Alright, so first I'm putting down my spacer piece. Kind of adds a nice finishing touch there, doesn't it? So I'm using a bolt, one of these split lock washers, to insert the bolt through the main positive. Again, being extremely careful and mindful of where the negative is at all times. And then that will get threaded into the bottom of the lid here. Again, they recommend using blue Loctite or some sort of thread locker on this. You don't really have a lot of room to work in here with these short wires. There is no way, like I can't even get my fingers under here to tighten this nut, let alone fitting a tool in there to tighten that down. Oh, I think that one's finally tight. Let's see if I can find where the wrench goes. I can hopefully tighten this down. Alright, so they're both finally tight, but man, that was a pain in the butt. There's no reason why they couldn't make those longer. They really just need an extra 4 or 5 inches on them. Alright, so now I'm ready to plug in the balance lead to the JBD BMS. Also going to plug in the passive balancer here. And I'm just securing the passive balancer with a piece of double-sided tape as recommended by the instructions. Though I really wish I would have drilled a hole in the plastic that I could have put a zip tie through. So before I close this up, I just want to make sure I'm receiving voltage on the terminals here. that the BMS is turned on, and I see 13.17 volts, so we're good there. And to secure the lid, there are simply 4 screws on the top of the case. And they do suggest using a hand tool and making sure not to over tighten these screws, because I guess you risk either cracking the case or pulling out the nut plate, if I had to guess. Alright, so we've got some more prominent positive and negative indicators here, just to make sure there are no mistakes. And then we also have our handles to attach, so I'll insert this plastic piece through the piece of rope here, and then those just go through the holes on the side. And then the bottoms of the handles just fold up underneath, and there's a little notch that they'll slide into. There you go. Alright, so we're now ready to charge up and run a capacity test of this battery. I did set up the app for this battery. It's just called SunFun Kits. It's in the App Store. On Google Play, at least, I assume it's the same on iOS. It is showing a capacity of 260 amp hours and says it's 100% charged. So I'm going to guess this BMS is not calibrated yet. I'm hoping when I do a full charge and discharge cycle of it, it's going to calibrate. So we'll just see what happens. And for charging this battery, I'll be using this 12 volt 75 amp lithium iron phosphate battery charger from Ames Power, and I purchased this from Current Connected. This is the first time I'm actually using this. I've seen a few other people use it, and it seems like a great 12 volt charger instead of the iCharger method I was using that only does 8 amps. So this does a variety of different chemistries. It does 12 and 24 volt, and it should charge up to approximately 14.4 volts, which I believe is 3.60 volts per cell. I've got the Anderson connector on both the battery and the power supply. Alright, I heard a relay engage. Grab my safety glasses here. Turn on! I was scared for a minute. I didn't hear it doing anything there, and then it finally started up, so. And I'm not seeing anything happening. We're sitting at 0.39 amps. It keeps turning on and off. Maybe it is at full state of charge already. On the voltmeter, I'm seeing 14.55 volts. But on the app, I'm only seeing 13.32. Wonder what's up with that. It's saying charging is not enabled. Let's go ahead and turn that on. Okay. And it switched charging off again. So what is going on? Alright, so this is the app I usually use for these JBD BMSs, and this one is showing overcurrent protection was engaged. So let's see what the configuration is set for on this battery. Maybe I'm just charging it too fast. So this BMS is programmed to trip overcurrent charge at 65 amps. That's a rather unusual setting. So I'm going to take a minute here to pause and go back to the documentation on the website and make sure and see what it says regarding the maximum charge current. Alright, so I did find on the website, it does say max charging amps is 60 and max discharge amps is 125. So I don't know why they have this set for 60 amps on a 280 amp hour battery. It should be able to do at least 125 through a 150 BMS, but you know, I'm not the one that designed this, I'm not the engineer, so instead of trying to push it, I adjusted this Ames charger down to 50% charge current, and we're going to give it a try again here. There we're at 46, that should be good. The individual cells still have a little ways to go yet, so we're going to leave this run until the high voltage disconnect shuts it down. Alright, and here's how the cell balance looks at the top end of charge. You can see cell number 1 is just finishing up there at 3.62 volts. And there's only 73 millivolts difference between the high and low cell. And there you can see we have over voltage protection. Alright, we've got our usual setup for capacity testing here. We're using an Android display, a Batrium shunt, and a 2000 watt inverter. The Batrium shunt is connected to a Watchman 5 and transmitting data to this display, where we can see voltage, amperage, wattage, amp hours, and watt hours. Oops. And for the load, I have a space heater. I'm going to run this on low, which should put approximately 975 watt load on this battery, which will be around a 0.27 C rate, I believe, when I calculated it out. So we'll just let this run until the inverter or the BMS shuts down, and we'll see what our capacity is. Here we go. Alright, it's loaded at about 72 amps right now. This will be a good test. I do expect it to increase a little bit, but like I said, we will be back shortly. So we're currently at 282 amp hours. It's still running for a bit longer yet. And here's a look at how the batteries look at the lower end of the state of charge. These are some pretty nicely balanced and matched cells. I'm quite impressed. 286 amp hours. That's 6 amp hours over its rated capacity. That is incredible. Alright, so the conclusion from this is I really like what this company is doing by building this DIY battery kit. Many of us are going out and purchasing these cells from Alibaba, AliExpress, other places around, planning to build a battery, and then we get the cells and we're not exactly sure how to assemble them. But I do think there is a little bit of room for improvement. As you saw, the cables that are pre-crimped for connecting the cells to the BMS and the BMS to the battery terminals on top here really are a bit too short. And what ends up happening is it's difficult to get your tools under here to make these final connections during assembly, and you end up bending the wires at sharp angles, which could result over time in those strands breaking But that really is an easy thing to solve. All they really need to do is make those wires just a couple of inches longer, maybe if they were 4 or 5 inches longer. That way you have enough room to kind of loop them around in there. Or maybe even better, just use some silicone insulated wire, like a pair of number 6 gauge for each connection. And the only other thing I noticed in terms of something that could be improved is I don't know why the BMS was pre-programmed for 65 amps and advertised at 60 amps. That's a 150 amp continuous BMS, so in my opinion that could probably be turned up to 125 amps charge and discharge for these particular cells. And of course I don't know why it was programmed like that, so maybe the manufacturer has a reason, so as always I would check with the manufacturer before making any changes on settings like that. There's a lot to analyze when we start talking about price of this. The base kit starts at $176, and that pretty much includes the plastic case, some of the hardware, and some of the plastic brackets. And then you can add on any extra items you want, including the BMS, the balancer, different brackets for different spacings of cells, all the wiring, and you can even pay them to pre-assemble your battery if you want. If you decide to purchase the kit plus the BMS, and the BMS includes the pre-crimped wires, you're looking at $310. I personally would not spend the extra money on either the active or the additional passive balancer, because once these cells are balanced out, they should remain balanced over the lifespan of the battery as a whole. They should not be drifting apart. If they are, in my opinion, that's a problem with the cells, not something a balancer is going to solve. And like I said, they do sell these cells. I get asked quite frequently where in the US people can purchase these lithium iron phosphate cells. Based on what I've seen here, I feel SunFun Kits is an excellent place to go for that. They are selling a 4-pack for $795, so that's just about $200 per cell. And when I tested them, they're rated for 280 amp hours. They tested at 286 amp hours, which is 102% of their rated capacity. So all in all, if you go to purchase one of these yourself, the kit and the cells, you're looking at about $1,061. And that does include free shipping and a 10% discount code, which you can find in the description of this video. And that will calculate out to $279 per kilowatt hour. In comparison, one of the best, cheapest batteries on the market is the SOK. So they are selling a 12 volt, 206 amp hour battery, and that calculates out to $390 per kilowatt hour. So if you're okay doing a little bit of assembly yourself, this is definitely the way to go in terms of price. So I think that's where I'm going to wrap this up. If you think there's anything I missed or anything you want to see more of with this battery, any questions or comments, you can leave those below as well. I want to thank SunFun Kits for sending this out to me for evaluation and review. And before you go, please don't forget to hit that like button. Thanks for watching.